turned out by using an analogy to gravity, where we had an object at point A and an object at point B. And we indicated that in terms of gravity, which object would feel a stronger force? B. Why? It's closer. Yeah, absolutely. And so then we've taken that analogy and we set out a couple of electric charges. So let's make this one positive, this one negative, this one negative. Which location is going to feel more electric force? Yeah, B. Why? Yep, it's closer. So we can use Newton's law of universal gravitation or Coulomb's law to recognize that because they're both 1 over r squared relationships, as you get closer, you get stronger forces. Okay. Now, we then went on to talk about energy. Which of these spots, A or B, for gravity would have more gravitational potential energy? Okay, I've got two different answers. Why B? I want to know which one has more energy. Yeah. Yeah. Okay, so change our instance to A because it's further to fall, and you said A originally because more time for energy to build up, or to change to kinetic. Yes, it does. So because height is the important factor that we're looking at here, yeah, A is the right one. A is going to have more gravitational potential energy. Okay, now in terms of electricity, which one's going to have more energy, point A or point B? When I release these charges, or I release a charge here, and in a later time I release a charge here, which one is going to show that it had more electric potential energy? I'm going to change up the question just a little bit. If I do that experiment where I put one there and I release it, and later time I put one there and I release it, which one will be moving faster right before it swings by the positive charge or hits the positive charge? Why A? Say that again? You said A would be moving faster. Okay. Why? Shorter path? Yeah. Okay. Any other answers? A, because it has more time to accelerate. I like that answer. Or A, because it's got further to fall, if you want to keep the analogy to gravity. Absolutely. So it doesn't matter if we're talking about gravity or if we're talking about electricity. A is going to have more energy here because if we think about, well, which one's going to be moving faster, the one further away would be moving faster, have more kinetic energy, and thus have more energy, potential energy of the respective types to start with. All right. I'm going to change up the problem just a little bit. Positive, 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 A, B. And in this case, which one is going to have more energy, point A or point B? Note that these are all positives. Why B? Yeah, it's going to be repelled faster. Or if you want to think about it like a slingshot, A is pulled back just a little, B is pulled back a lot, and when you release B, it's going to launch out with more energy. So in this case, EPE is greater. Now, because we did discuss direction, the sign of the charge here was important. However, we never at any point discussed the magnitude of the charge, and at no point here did we discuss the mass of the charge, or the mass of the object, because here, does the mass of the object matter? Does the mass of the object determine how fast it's going to go when it hits the Earth? No. Think back to conservation of energy. We saw over and over and over, let's go from GPE to kinetic energy, showing that mgh was equal to half mv squared, and what happens to the atoms? They cancel. So really, we could have done problems when we talked about conservation of energy where we didn't use mass at all. And actually, I think you guys had a test question where I didn't give you a mass of an object, and some of you kind of freaked out about that. And others were just like, yeah, so I don't have the mass, I cancel it out, no big deal. Okay. So really what's important isn't what the object is, but rather how this central object warps the space around it. So we've talked about m as the mass of our object, h is how far up it is, but g we just redefined in the last few weeks as not just 9.8 meters per second squared in acceleration, but a local gravitational constant, or how much mass warps space at a specific location. So really, rather than talking about GPE, we could talk about GH, which we would call gravitational potential. Gravitational potential, which would be equal to GH. So if I want to talk about this point in space right here, where there's no objects currently, I could talk about its GH value. Because no matter if I put in a calculator into that space, a battery into that space, a remote into that space, they're all going to drop from there, be going the same speed when they hit the table, right? They're all going to have the same amount of energy per kilogram the object has when they're in that location. So this is an amount of energy per kilogram at a point in space. So when we talk conservation of energy, one of the things that may have been more helpful to us is to have talked about a unique property of a point in space, GH, as being its gravitational potential, or how much energy could something have if it were placed there. This is a property of space, not a property of the object we put in that space. Okay? So, and via Einstein, we can understand that as something to do with the warping of space and how it's curved at that location. Questions on that idea from gravity? It's pretty abstract, but we're feeling okay with it? Okay, now we're going to make it electricity. How do I determine the electric potential energy of a charge? How do I determine the electric potential energy of a charge? Well, let's do it slightly differently. Everything else between gravity and electricity has kind of mirrored itself, right? Everything's looked pretty identical. We just kind of changed some letters. So if I was calculating gravitational potential energy, it was mgh. Electric potential energy, what would be the electrical equivalent of mass? What would be the electrical equivalent of mass? Charge, good. I'm going to skip G for a second. What would be the electrical equivalent of height? Distance. I mean, we could probably still use height, but or radius would actually probably be good. I'm going to use D for displacement. Though height's fine, we just are specifically talking about a vertical displacement. So not terribly different. Now here's actually the hard one. What would be the equivalent, the electrical equivalent of G? What would be the electrical equivalent of G? Nope. So let's try this. How else can I define G? What are the things I can call it? I want to point out, okay, it's gravity. What about gravity is it? It's not, no, this little g is not a force. Say again? No, this is a little g. Say again? can't hear you. Okay. You might have been right. I just couldn't hear you. What is little g? Give me the easy answer. That you learned in gravity. Give me more. That you learned in October. 9.8 meters per second squared. All right, good. It's an acceleration. We gave some additional definitions to it 2 weeks ago. What were some of those additional definitions that we gave to little g? What is 9.8 meters per second squared? Sure, it's an acceleration. How else could we define it, though? Find something? So when we're talking about little g, we could be talking about the acceleration due to gravity, or we could talk about it in terms of how much space is bent. Now, we did give it another name beyond that, and that it was the local gravitational field. Okay, is that sounding familiar? Anybody see that on their notes in front of them, just didn't want to say it? Okay, all right, so if this is the local gravitational field, what can I make as an analogy for the electrical version? Local electric field, which we gave what variable in the last unit? Go ahead. Take a guess. Well, that's force electric. I want electric field. K is a constant, similar to capital G. It is E. E, which was electric field. All right, so we've got Q, charge, capital E, which is electric field. Remember back to last chapter, that's how much a charge influences the space around it. And D, how far away from the original charge you are. Okay, if you're not sure about what an electric field is, look back through your notes from last chapter. Okay, it's a very key concept to understanding this section. Okay, so we've got an electric field. Now, if we want to continue to run our analogy, well, in this one, we canceled out M, so we're just going to take out Q for the moment, and we're going to talk electric potential. Now, electric potential energy is the amount of energy a specific charge has at a location in space. Now, what we did with gravity was we removed the specific object, and so we're going to do so with electricity as well. And rather than talking about a very specific charge, we're going to talk about how the space around a charge is manipulated. And now we get electric potential is electric field times displacement. And last hour we made a joke about how Ed now has potential. If you know Ed, that's funny. All right. So when we're talking electric potential, we're not talking about what's going on for this object. We're talking about the space that the object's located in and how much energy per charge it has at that point in space. And amount of energy per Coulomb at a point in space. So you'll notice the two are similar ideas, and both are talking about a location in space. They're not talking about what object you put in that space. They're talking about a location in space. And this is significant to us because when we start talking about Officer Johnson's taser, he referred to this concept repeatedly. He didn't call it electric potential, he called it voltage. Electric potential is voltage, okay, measured in volts and using the symbol V in both equation and unit abbreviation. So when we talk about 50,000 volts of the taser, what we're saying is that every charge in the taser has 50,000 joules of energy per charge that it carries. So a volt is equal to a joule per coulomb. So he talked about it in terms of the pressure behind the charge, and he said he really wasn't a fan of that analogy. It works, but I'm not a fan of it either. And what we're really seeing is how much energy does each individual electron pack. Okay? And the more energy each one's got, the further it can go, the more work it can do. So the higher the voltage, the more work can be done. Higher voltage means more energy. And more work that can be done. Now, the property that then he then talked about that was dangerous and that can cause damage is current. Now, current is the flow of electrons or the number of electrons or amount of charge that passes through a given location per second. An amount of charge that passes through a location per second. A location per second. So calculationally, that would mean charge or coulombs per second, which is an ampere. Alternatively known as an amp. Okay. So while voltage is the amount of energy each individual electron is packing, current is how many of those things or how much their total charge is carrying pass through a specific location per second. Okay? Now, earlier last month, actually now, we worked with the Van de Graaff generator. Van de Graaff generator can generate up to 120,000 volts of electric potential. Meaning that every little charge on here at 120,000 volts, I don't want to say of energy, but of energy per charge. So they could, each one could do a lot of work, which is why they could jump so far out here. However, there's not a lot of current. There are not a lot of charges. So the individual amounts of charge were very small, and therefore I can sit here and exact repeatedly, and I'm really not worried. Right? Not a lot of charge, not a lot to be done. A lot of energy per charge, so that you go far, that you do a lot each individual one, but as a group, not a whole lot is going to be done. All right, so let's play with the opposite. So this is a 15,000 volt transformer. This would definitively kill me if I played with it wrong. So what this is typically using, you know how you see the big gray boxes on telephone poles? That holds one of these, or multiple, depending on the individual transformer location. And what this does is this takes the 120 volt output that we have here, which you already know, don't stick a fork in it, and ramps it up to 15,000 volts. So now we're giving a lot of energy to those individual electrons, and we're running at wall current, which is enough to kill you. So we're going to take down wall current just a little bit, still plenty lethal, and ramp up its ability to make jumps. What that means is now we have electricity that has both the energy to do stuff and lots of it, so they're in large numbers. So we're going to go ahead and turn that on and play with it. The device I have up front here is a Jacob's ladder. Anybody seen the old black and white Frankenstein? Yeah, that's one of those. This is one of those things that he has running in the background. And what it does is it's got about a 1 centimeter gap. Actually, it's closer to half centimeter gap at the base. And because we're running 15,000 volts of electricity, 15,000 volts is enough energy for the electrons to jump from one side to the next. When they do that, they ionize the air in between, meaning that they strip specifically the oxygen of its electrons. They remove the electrons and therefore create a conducting ionic gas, or a plasma. That plasma is therefore conducting, and additional electrons can travel through it quickly. Now, as it heats, it rises, because hot air rises, and we'll see that band getting bigger and arcing larger distances.
So if it strip the oxygen from the molecule,
Strip the electron from the oxygen in the molecule. Yeah, so if I were to fill this with nitrogen rather than oxygen, yeah, it would have some different effects, and might require a different voltage in order to jump that. And we would potentially have different byproducts in the end. This is actually going to be creating ozone while I have it running, not breathable oxygen. So plug it in. So again, you see the plasma rising quickly as it's going through that conducting oxygen, or conducting ionic oxygen at that point. Ozone is reaching the top. And arcing between the two. It's able to arc because it has a high voltage. I'm not touching it because it has a high current. Okay, let's change that. Take off the protective casing. Come on. Perfect. We're going to pass this one around. I'll bet up to the light. And I'll do that in a second. Okay. Going to pass that one around as well. What you should be able to see are a whole bunch of little burn holes. Those individual little burn holes are actual discrete electrons punching through the paper itself. So you can tell them that this is not actually a continuous flow of something, but actually individual electrons traveling one after another very quickly. The electrons have enough energy that not only can they jump through the air, but they can also burn a hole in the paper. Now, if I didn't run that through there, I'm going to sit for a little longer. Let me just start real quick.
So you said it was electrons flying, like going one after the other.
Yes.
They follow each other.
Yep.
So were they moving like a horizontal or?
Yeah, basically the electrons are going like this. That blue beam that you see, that plasma, is the directly after that. Okay. Others? Okay. Again, this one's running at 15,000 volts. The dangerous part is that it runs out. With 0.3 amps. To give you some idea of scale there. Now, I'm going to try to get my numbers right here. 0.0005 is a slight tingle. That's when you can kind of feel it. Tingle. 0.005 amps is considered painful. Remember, right? 0.008 amps is loss of muscle control. 0.015 amps is deadly. All right. For perspective, this is running at 0.03. So plenty dangerous. And just to remind you from Wednesday, the taser ran at 0.002 to 0.03. Below that for the pain, below that loss of muscle control, which goes to, wait a minute, does somebody lock up and fall on the ground then if it's so much than what's supposed to take out muscle? Yeah, it was mimicking brain waves. And it was operating the same wave function the brain sends. So it's less about raw amount of electricity because we're significantly under that. And it was more about sending it in the specific fashion in order to your brain and clog out any kind of signals that your brain should be trying to send or muscles trying to receive. This one actually is one of the only demonstrations that I do that actually makes me slightly nervous. Because that's the amount of it takes to just kill me. So, that actually makes me a little nervous. But you run paper through it. That's a good idea, right? Take off the protective casing. I used to have a bigger one, like bigger. It's in my house. So talking about current, talking about voltage. Next one then is the combination of the two. When we combine voltage and the current, that's where the power to actually do something. So I times V, what we're looking at then is coulombs. I'm just going to write the abbreviation. Coulombs per second times joules per coulomb. You'll know coulombs cancel, and I get joule per second. And if you recall back to November, we've already worked with a joule per second. What is that? It does have to do with power. This is power, which is measured what? I can't tell if the answer is just like looking at the fact that I've already handed it out twice. Say again. Watts. Okay. So this is power. So we have power equals current times voltage. So if we wanted to talk about a simple 60 light bulb, a 60-watt light bulb plugged into their standard 120. Plugged. My hand is not on correctly. To a 120 volt outlet carries what current? Simply using P equals IV, we can determine that one. So 60 equals I times 120. Therefore, I must be 0.5. So half of the current running through a 60-watt light bulb plugged into a standard socket. Probably way higher than in even this thing's taking. Okay. All right. Couple things about current. Typically in your house, current can get up to 15 amps. Household current. Max is 15 amps. We'll talk a little about alternating versus direct current at a later point in time. But then the next part here is if we're working with current and voltage, why don't we, how are they not always just running very high values? The last piece of the puzzle here that we're going to work with is resistance, which is the impediment to the flow of current. Impediment to the flow of current. Okay, resistance is measured in ohms, which uses the Greek symbol omega. Measured in ohms. and is on an equation. Yep. There you go. Okay. Some of you who took science probably might remember Ohm's law, which is a relationship between I and resistance. Some of you may have learned it in an class. I'm not going to direct it, but if you remember it, awesome. We are going to be working on a lab tomorrow that is going to show the relationship V, I, and R are going to determine what the between those three. If you have knowledge, you're welcome to use it as part of your hypothesis. Otherwise, you've got the notes we've taken. Okay? But by the end of the lab, you will have definitively created an equation for these three variables. Now, in order to do that lab, you're going to need to know how to use a multimeter. And a multimeter operates on two separate principles. And the first principle is that in a circuit or in a singular loop, current is the same at all points. So if I have a battery and I connect it to a resistor, battery, if you know these symbols, feel free to use them. I'm going to teach them at a later point. And I want to going through here. All I want to do is connect it to my ammeter such that it makes one loop. And the current at all points in that is the same. At all points in a loop is the same. And if you think about it in terms of like, I don't know, a highway where cars can't get on or off, they just travel in a loop. I mean, sure, they'll pass each other, but as a whole, they're just going to keep moving around in circles. Any electron that goes in one spot has to moving through another point. It doesn't have another choice. The alternative to this is how we actually measure volts. So again, with a battery, looping up and over to a resistor. So I'm going to close this one and measure how much energy per charge the resistor is using. I want to connect my multimeter here in a separate path that goes around the resistor. And this would be my voltmeter. So the current, one loop to measure voltage, a secondary loop that goes around the resistor, or whichever object you're trying to measure. And I could write here, volts are the same across parallel branches. Volts are the same across parallel branches. And what I mean by that is that when they have a choice and those two choices meet back up, the voltage across this branch and this branch must be the same. Meaning that the amount of energy the electrons carry here and the amount of energy the electrons are carrying here are the same, and they're returned back to this point having used up the same amount. Good? Other questions about this one? So, this chapter is significantly different from the other ones in terms of how the test works. So on tomorrow's lab, you're going to be working with a multimeter, and I know sometimes in a lab, you'll have one person who does the hands-on stuff and knows how it's working. Well, make sure that that's you this time, because this is, for this chapter, I do not do a standard written test. Instead, for this chapter, the way I do it is you find time outside of class, before or after school or during one of my prep periods, any of those work, that you're going to come in and I'm going to have a couple of circuits set up for you. You're going to use a multimeter, measure a few different things, calculate a couple of properties about the circuit, and then explain to me how a couple of concepts work. for the circuit itself. So it's a very hands-on, one-on-one test. It is not a written test. Okay, so that means you need to make sure you understand how those things work and be able to explain it to me or work through it yourself. So any measurements taken tomorrow or Thursday on your lab, make sure you understand how they're being taken and that you can replicate it. Questions?